or from one point to another point, it's going to rapid and then plunge in. Again, some people have given me elevator operation. Well, it's not manufacturing, but I've given you the benefit of doubt. Pipe bending, strictly speaking, elevator operation can't be open loop. It's not predictive. You have sensors inside which are going to control which floor and so on. But is it an example? I would say it's not a good example. Punch press, point to point. Number 8, in addition to the standard 3 degrees of freedom provided in CNC machines. We have gone through this, I've shown you videos. The best example would be an indexing table on the bed. Ability to pitch or a roll or a yaw, giving you additional degrees of freedom. Some have said it can be built into the spindle. I said yes, but it is more difficult and rare. But I've given you, if you had given that as an example. What type of feedback is necessary for a servo control CNC drive system? How will it be used in the control implementation? Well, you got a sensor such as an encoder which gives you the position. Then first derivative will control the velocity, and second derivative is controlled acceleration. I've said this many times. How is it used in the controller? Position, go from this point to this point. The velocity is the feed rate, and the acceleration is start, accelerate, attain the velocity, decelerate, where that information is required. So that's the key to the midterm test question paper. Any questions from you?
Yes, Professor. I put drilling and punch for 7, and you gave me a 0 on 4, so I'm just a little confused.
Which question?
For number 7, you said suggesting manufacturing applications for a point-to-point type of controller. I put drilling and punch, and I got a 0 on 4.
Okay, what is your name? I have to go back and check your. I have the booklet.
Wesley.
Wait, let me get a pencil, I note down, and I have it on the other side. I will tell you during the lab. Okay?
Sure. I do have a few other questions. Can I meet with you in the lab?
Yeah, you can speak to me in the lab.
Sure. I'll join Cisco WebEx.
Yeah.
Okay. Thank you.
Dr. Ballard,
Anybody?
explain the point-to-point controller.
Yeah. Can I can hear you.
Oh, sorry. Can you explain what a point-to-point controller is again?
Okay. Take the operation of a drill. You're going to go from one point to another point, and I gave you the example of Dominion Bridge, 1,000 holes to be drilled. You don't do any interpolation at all. You go from one point, like what you did, the 4 holes being drilled on the housing. It just goes from one point to another point in the air. There is no interpolation, nothing as rapidly as possible, and then dips down. That's the point to point.
Okay, thank you.
Okay. Anybody else? No? Okay. In fact, in point to point, why is it going rapidly? Well, if you're going to drill so many holes, you're going to waste too much time if you're going to spend in the air interpolating between the points at a lower speed. Not needed at all. It's not in contact, it's moving rapidly in the air. Okay. Okay, that's the question paper, and I'm going to close it. And cancel. Those who might have come late, at the top is the average 70.5 or 54, and the lowest and the highest out of 50. Okay. Compared to this, last year's high was 47, And the low, I don't remember, but there are some lows, the range in which it's indicated. Okay, let me close. I might minimize. Oh. Okay, I am back. Okay, can you see the PPT slide?
Yes.
Okay. I since I don't see your screens, do you see the little window at the bottom showing participants on your screen?
See the full slide.
You see the full slide. Okay, because I sometimes struggle to move it out of the way. Then maybe I don't need to do it. Okay, so very quickly to recap, we are talking about a ventilation system. So bit of this is going to be part of the project 3, and then there will be more bells and whistles on it. So we have a process, and I gave you the example of a overhead projector or a slide projector or a multimedia projector where there is a bulb producing a lot of heat, and you need to take the heat out of the casing as well as keep the temperature of the bulb at a reasonable level. So you need a fan. So ventilation answers to the I need to get the pen. What happened to my pen? Okay, my pen probably will come back at some point. Okay, so ventilation represents the fan. The machine, let's take in the case of a projector, the bulb. So a fan and a bulb will be the outputs. They have to be controlled. Then, to understand the problem, well, for a period of time, when the process is shut down, in this case, when the bulb is put away, lecture is over, you want the fan to keep running for a period of time. Could be 3 minutes, 6 minutes, whatever the designer decides. Then it shuts down. Okay? So that's the problem statement. Now, looking at the problem, this is a very simple problem. Not very many things are involved. You must identify what needs to be controlled as an output and what needs to be as an input to the controller. And you don't have to worry about what type of a sensor it is at this point, but if you're going to implement, you got to look at that too. So right now, there is an on-off switch. That is an input to the controller to turn the process up and must state the type of switch. It can be a permanently on and a permanently off, or it could be momentary on and then off switch. Makes a big difference in terms of the truth table and the logic equations. So you must understand what the assumptions are. Output, there is a fan and the machine. In the case of a projector, as I keep saying, the fan is the ventilating fan and the machine is the bulb. What is the condition that has been imposed? Fan must remain on for 3 minutes after the system switch has been turned off. The question that normally comes up, if the fan is turned on for 1 minute and then you switch it off, should the timer keep it going for 3 minutes or less? If you understand heat transfer, yes, the longer you keep it on, more heat is developed and then it reaches a thermal equilibrium, after which it doesn't matter. But no manufacturer involved with the fan in overhead projector will want to put all those type of controls where you're actually measuring the temperature inside and then you're putting it as a loop. But in more complex processes, yes, you will. Okay? So in this case, well, no matter what, you switch on the machine, which is the bulb. If it is 30 seconds or 1 minute or 5 minutes or 1 hour, doesn't matter. Keep the fan going.
Hey, Dr. Bella, you're muted.
Okay. Can you hear me now? Yes?
Yeah. Good now.
It's a Microsoft headphone. Has a little hidden switch for muting. So if I accidentally put my hand or whatever, it mutes me off. So I have to now be very careful. See, I don't have a feedback unless somebody tells me. So we are going to have the timer going for 3 minutes no matter what. Identify the variables. A. Letter A. I tend to use A, B, C, D, E, F for inputs and starting with U, V, W, X, Y, Z as outputs. Okay. So keeping that convention, there is no convention. That's my convention. A, identified as in green, is an input on-off switch. Permanently on, permanently off for this problem. Capital B, red, is an output, the machine or the bulb or whatever. And the D is the fan. Okay. Do we go to the truth table? Or, yes, you can go to the truth table. I'm going to show you variations. So in this problem, I'm going to go and first put the timeline diagram to understand this problem before I start working on the logic. One input and 2 outputs. So in this case, I didn't use the XYZ, I used the ABD. So timeline diagram shows the status of the inputs and the outputs with respect to time, as we looked at it in the last lecture. So I am going to start with an A, which is the power on off. At time interval 2, in this case it appears to be a minute. At the end of 2 minutes, exactly at 2 minutes, I switch on the power. Let me see whether my pen has come back. No, it's working as a mouse. Where is it hiding? Somewhere here there must be an annotation button. Okay. Here. Let's go. So A comes on. Machine must come on right away. So A and B rise at the same time. D, the fan, must come on right away. So A, B, D are in sync. Then somebody decided to switch the power off at the end of 7. minutes. When A goes down, the lamp or the process comes down right away. But the logic required here, or the problem statement says, you must keep the fan on for another 3 minutes. So look at the period from 7 to 10. The fan alone is going, which is the D. And at the end of 10 minutes, fan collapses. It has done its job. Then go to the interval 16. This is just an example. You can go with another timeline diagram of your own time inputs. So at the end of 16, not at the end of at the beginning of 14, I switch on A. I get it activated. But in 1 minute, I switch it off. So B comes on. In 1 minute, it also goes down. From 15 to 18, the fan keeps going. So, questionable. Is it needed? Should it be proportional to the time? We said in this case, I am not going to make the problem complicated. And depending on the process, in majority of cases, it is unlikely that the time element will be made proportional or be a function of the temperature inside. So for example, if I locate a temperature sensor inside as the machine is running and the heat is building up, well, you keep the fan going, but measure the temperature. If the process was shut down very quickly, obviously the temperature would not have risen. So use the temperature sensor to control the time element. Can be done, okay? But not in this case. Then look at the period from 21. What is happening? Somebody is monkeying around with the switch. Up, down, up, down, up, down 3 times. Looks like somebody is testing the machine after it was fixed. The machine comes up, goes down, comes up, goes down, simply yo-yoing with the switch input. Okay? So A and B are following each other. The fan, because of assumption, did it come on? Yes, it came on when A and B came on. Keeps going, but when both died, it keeps going for another 3 minutes. So the timeline diagram explains to you or gives you a visual understanding of the problem. Okay? Good tool to use to understand better based on what the problem state is. Now, you can go to a truth table where how many rows will be? You have an A which has 2 states, a 1 or a 0, right? So how are you going to use the truth table to analyze the problem? You have 1 input, either a 0 or a 1, and 2 outputs, which could be a 0 or a 1 each, right? So if you deal with this kind of a problem, this stuff I'm going to do now may be a lot easier. If not, you can go to the truth table using the output as a feedback, as an input. So you can put A, B, D as in the truth table, 2 power 3, 8 rows, 3 zeros at the top and 3 ones at the bottom, and I will work out all the magic in between. Okay? But you have to decide to bring on the output stage, you have a B and a D. So each row will tell you what will happen, right? So in this case, I'm going to show you another procedure that can be used to construct the logic diagram. Reverse engineering, work backwards. In many simpler problems, this is actually workable easily. So when I work backwards, output variable B, which is the fan or the machine. I don't know what I stated. Let's go back. Output B is the machine and D is the fan. So remember that. Okay. Output variable B must follow input variable A. So if I use a diagram, I can go directly connect the two. Well, I will show you the next slide. Output D, the fan, is not like B, has two options. What are the two options? One, coming instantaneously, moving with A, or when the timer has expired. Until that time, keep the output D. So whenever you see two alternatives, you know there is an OR operation involved or OR logic. Okay. So start like this. Connect A to B as the line shows. Okay. And then the second one is a little R connected to the output D. Because there are two alternatives, I put an R circuit with the question mark as to what should be their input. Okay. So we are working backwards using the logic statements to construct the logic network diagram. So when the system is turned on, which is the A, B comes on as well as D, the fan should come on. Okay. The other control obviously is going to be a timer involved. Okay. So we have to bring that into the loop. So the second stage of the diagram, from the first, which is A, B, and then an R with a question mark, outputting D, one of the inputs to the R is the A. And the other input to the R is a timer. And I purposely shown it with the dotted line. Is it timer direct or something should be done? Remember, based on the assumption how the timer works will come into play here. Okay? So if I follow the assumptions that I made for the timer, the functioning of the timer is as follows. The timer needs an input, and the input, when it is sustained for the period that the timer has been programmed, will get the timer's output to be a true at the time expiry of the time, as long as the input is true. If the input collapses, the timer outputs will also collapse with it. That's why there's a little question mark as to what should be the input and should the timer's output be connected directly. The answer is no, but we have to go through the problem step by step. So the next slide says, only when the output timer has not expired, you want the fan to do its job. Only when the timer has not yet expired. There is a logic not involved, okay, on the output of the timer. So the R circuit shown here with the timer as the second input needs to have a NOT on its output. That's what is shown here. Okay, so that problem is solved. Now, how about the timer's input? What should it be going to? Is it going directly to the A, or is there something that's going to be in its path? Okay. Again, timer is not cumulative. Remember I said every time you switch on A, timer comes on and then boom, it goes away when its time element has reached the limit. Okay. So every time you make the input to the timer true, the timer is triggered. Assume there is some magical device inside, like the rotary timer that I brought, which is no longer used in very advanced applications. You have a little digital timer inside. Okay? So if you program a time into it, the digital timer is triggered when the input is on, and it'll going to start counting, okay, towards the 3 minutes. In PLC, you can go in nanoseconds, milliseconds, seconds, minutes, hours, depending on how it is structured. Okay? So I will show you when I show you the physical PLC being demonstrated in the lab. So we can program all kinds of time elements. If input is interrupted by off periods at interval of less than 3 minutes, means if I collapse the input, timer can play its role. It will simply go down, right? Based on our assumption. So we got to do something to bring that assumption into the logic diagram. So looking at the problem statement, if the system is interrupted by off periods of less than 3 minutes, okay, we don't want the timer not to do its job. It should still go for the 3 minutes. So what we have to do is to bring in another NOT operation in the input to the timer, okay, in order to do its job. So what we have here is a diagram which involves one OR circuit, 2 NOTs, and a timer, with the B and D as output and the A as the input, only one input. How do we know this circuit that is got or shown here works? Did I make a mistake? Let's see. Well, I got $1 million simulation that I'm going to show you. I developed this technique, not $1 million. I didn't sell it to anybody except to use it in this course. When there were no simulations option in PLC, there was no software. So in order to understand the problem, my hand simulation goes like this. You see a green 1 appear on the input A. Since A is connected to B, B should go fly to a 1. A is connected to the R circuit, so there is a green as one of the input to the R, which is the A, which has now become true. So we don't care what is the other input to the R, automatically D will come up to be true because it's an R circuit. Good. This far it is good. Now go through the other section of the logic diagram. A is 1. Input to the NOT is 1. Output from the NOT is a 0 because it's a NOT operation. Input to the timer is a 0. That means timer won't count at all. Output from the timer is a 0. Output from the timer goes to a NOT circuit, so output from the NOT will be a 1, which actually is redundant in this case. It doesn't have to, it's not doing anything. There are two inputs on the R, both are true. They don't have to be true, but in this case, both are true. So D happily will keep going. Now, let's assume A has become a 0. B will become a 0. That's what the process requires. How about the fan? The A becoming 0, one of the inputs to the R, the top one, has become a 0. The bottom is also 0, fan is going to die. But look at the operation of the NOT. A has become 0, input to the NOT is a 0, output from the NOT is a 1, input to the timer is a 1. What would be the output from the timer? Should be 0 until the time element 3 is reached, right? So it is shown as 0 as input from the timer at t equal to 0 to t equal to 2.9999 minutes. Okay, so if the input to the NOT is a 0, the output from the NOT is a 1. So the other input to the R will be maintained as 1 for 2.999999 minutes. That means D will be kept at 1. Okay. Then at 3 minutes, what will happen? The output from the timer will become true. Input to the NOT is a 1. Output from the NOT is a 0. Both input to the R are 0. D will collapse. Right? So my hand simulation says the circuit that is drawn at the top should be working. The easiest way to check, if you had access to the software of the PLC, throw this into the software, implement it in the software, download it to the PLC, and test whether it's controlling the two outputs B and D based on what you have done here. Okay. Every example that I will be using in this course, I'll go through the PLC implementation and show you, of course, online. But over the summer, I developed a number of different modules to show this happen on online mode. Okay. Now, if this circuit, you have a choice. If this is all we are going to do, just wire up the circuit and package it as part of the controller. But if you want to employ this is one of a very big loop of control. So we don't want to develop the hardware for it. We want to use a PLC or some logic controller. This is the logic network diagram. A shown as a capacitor symbol that is standard, generates B. A or not C generates an output D. What is that not C? What is C? We never talked about, we only talked about a B, D. Now I suddenly am showing a C. C is the output from the timer, which is shown on the last line. Okay? So, not C or A will generate D, not A will trigger the timer. Okay? So, this is this simple 4, 1, 2, 3, 4 lines long PLC program to implement the ladder logic diagram for the ventilation system. Any questions? Usually, the questions that arise, if the input to the timer collapses, how is the timer going to be powered? Will it also not collapse? Well, remember, in all these controllers, there are always power that is supplied continuously through a battery backup or through other means to keep the critical circuits still alive. The program won't be running. The simple example I would give, when you pull the ignition key off or switch off the ignition, depending on how the car is operating, ignition key or a button, everything collapses, the engine collapses, the lights collapse, and whatever that collapses. And as you walk away with the key, if it is auto shut off, the door locks after a few seconds. Okay? Then you can remotely open the door or remotely get the horn going. Where is the power coming from? Part of the circuit is still getting power from the battery. They are always alive. That's why if you don't drive your car during winter and you don't pull the battery off, one cannot assume, I've not driven, so the battery should still be good. Well, two aspects are coming into play. One, your temperature outside, going to minus 30, the battery automatically loses its capacity. And the second one, even before it reached that stage, probably you drain the battery off because many of your consoles have a hidden power to keep things alive. So you have to assume the timer in a controller, which is a critical part, along with the processor, because in the PLC, when you pull the power off, the programs don't get killed. They are alive, right? So that's how you should understand how power is kept. Same way, when you take the home security system, if you have one in your house or one in your apartment or wherever you go, there is a 12 volts battery, for example, in my house in the basement, which the home security people have put it in, which is always charged to its full level and is not required to be coming into play. But when the power goes down, the battery kicks in and keeps the operation of the home security system intact. But if the power goes down for 12 hours, 13 hours, 15 hours, or whatever hours, the battery will slowly be drained. Eventually, the battery also will go down. That means your home security system is no longer functional. Okay? So that's the usual question that comes up. So you have to understand that's how you have to interpret. Now, I gave you one solution. You can come up with another solution with some more assumptions. So in PLC problems, there are many correct solutions. Every one of them should meet at the end with the same result. Okay? So you may come up with a program with the 4 lines, Somebody else may come up for the same problem with the 8 lines or 16 lines. Obviously, 8 and 16 are not that optimal, but they're also correct solutions. Okay? Sequence of the rungs are not going to make a difference in this case, but I said before, in some cases, yes, they will mess up, and we will look at one such case.
Hey, Dr. Bala,
Yes. Go.
back to the slide for a little bit. So I can set up-
Previous slide.
Yeah, with the ladder logic there.
Yep.
So in that second run there, does that not mean that once C is not true, it's the timer is no longer running, that D will be true?
Okay. A is true.
Yeah.
D is on. A or not C true. D is on. Let's say A is true. C is not true. Timer has not expired. Timer has not expired. That means the output C is still true. No, output C is not true. When the timer is counting down, in our assumption, okay, when the timer is counting down, there is no output from the timer. Do you follow?
Sorry, do you mind just repeating that?
When you have a timer block, the assumption that we have made, it needs an input. Okay, there is an input to the timer. When the input is on, the timer's output is 0 until the timer comes down to the programmed time. Then only it
Right.
comes up, right?
Yeah.
So here, when A is triggered the timer, what will happen? The timer will be sleeping for the period of time, 3 minutes, 30 minutes, whatever, nothing will come out of the timer.
Yeah.
Right? When A is on. When
Right.
A is not on, okay, when A is on, at the end of 3 minutes, the output from the timer is true. Correct? So,
Yeah.
in this case, let's say A is true. The timer, fortunately, my pen, is it still going to not work? No, it's not working. So, when A is not true, which is the third line, the timer would not go anywhere. The output from the timer is 0. So, if the timer's output is 0, a variable C should be 0. Right?
Or when A is not true?
Yeah, when A is not true, timer is not even programmed.
Yeah.
It's not counting. So the output from input to the timer is a 0, output from the timer is also a 0, which is happening in the third round. Now, if A goes to true, the input to the timer is 1, output from the timer is a 0 until it is kept alive for the whatever you have programmed in the timer, 3 minutes, let's say. At the end of 3 minutes,
Yeah.
as long as A is still alive, the timer output will come out as 1, right? So C will become 1.
And
Now go back to the second rung. A collapsed. I switched off the power. What happens to the not C? Is it on or not? Is not C true or not true? A has collapsed.
yeah,
Okay. What happens to the timer?
timer switch on.
Because I have in the logic I have incorporated a not. Remember? Going back to this logic. A is connected to a NOT circuit. So that's what we are incorporating in the ladder.
Right.
Okay, so if I go with that diagram, the NOT C represents the output from which one? Yeah, from the timer.
Right.
So indirectly, we are bringing the NOT circuit of the logic diagram into this as a implementable solution.
Yeah.
Okay, so it should work. Do the hand simulation. I have no clue. I would have done it. My pen is working like a mouse right now, not as a pen. Okay, was working. I tested it this morning. You saw me write on the Word document, but now who knows? Okay. Ask again next class if this is not clear in your head, because I want you to make sure you understand this solid. The problem project 3 will require no confusion about these in terms of timers and counters and so on.
Good. Thank you.
Okay, but there are many correct solutions, blah, blah, blah. Sequence is not critical in this case. And I said exceptions do happen and will come up later on. Now, I'm going to go into another example. We all have heating systems at home. How does it work? There is a furnace, obviously, which when temperature goes below the set limit, kicks in, heats a condenser, and when the condenser is heated, you pass air over it with a fan, and the heat is extracted from the condenser by the air, and the air circulates in the house. And when the temperature reaches the steady state of whatever you have programmed, the flame goes down, the fan will go down, and you no longer have circulation unless you have a twin speed fan, which goes into a high gear or high speed when the heat has to be extracted, and then switches off to a low speed when you no longer require the heat to be extracted, but you want the circulation in the house to be maintained of resident heat inside the house being pulled through the furnace even though it's not heated. Eventually, it'll start cooling down. We are going to look at some similar example. Now, modern day furnaces have become pretty complex. If you walk in your street, residential street, when it is very cold and everybody's furnace is on, just stand in front of one house for a few minutes when the white condensation from the top is coming. Observe how long does it come and then becomes nothing, and then it comes again. This time, uh, let's assume in the first house you observed, it was coming for 10 minutes, then it shuts off for 15 minutes, and then it comes again for another 10 minutes. And the house next to it, it comes on, off very quickly. Okay. Now, you have to question, what is the difference? Why is one having a different behavior? Well, the one that comes on for a long time and then goes down idle for a long time is an inefficient furnace. Okay, low efficiency furnace, as they call, or it could be mid efficiency. The one that comes on off very rapidly is a high efficiency, but If it is a high efficiency furnace, the exhaust doesn't go through the roof. It is on the ground level, so you may not see it. Okay? What is the logic behind all this? Well, this is the operation of a real furnace at home. I'm talking about a high efficiency. You set the thermostat to 20, 21, whatever, Celsius. Okay? These are all digital thermometers operating on 24 volts or 12 volts or whatever. It's not 110. On a high efficiency furnace, this is what happens. When the temperature goes below, you set 20, it will kick in even at 19.9. Very short bandwidth. Okay? It'll come on. The first thing it'll do is to not switch on the fan to the condenser, switch on only the flame. Now, they all have electronic ignition. So it'll keep sparking to light up the flame, but to light the flame, the gas valve must open. It is never left open inside the furnace. Outside it is left open. So when the gas valve is opened, using some servo-controlled motor or a stepper motor or whatever they have incorporated in the design, it opens and allows the gas valve, sorry, not gas valve, the electronic ignition to spark. It's sparking system, not a lighted flame. So when it sparks, the gas that is coming into the chamber will ignite at some point. It's like for car engines, the spark plug technology. Okay? So when it ignites, good. It switches off the electronic ignition because why? There is no need. Your ignition has come on. But there is a flame sensor which is looking at the flame to make sure that the flame is sustained during the time when your condenser is heating, right? Now, when the condenser is heated to a certain level, normally it'll be in the room temperature. Now you lift it up because the flame has come on. Only at that time the fan will kick in, because these are all aspects of the high efficiency furnace. It wants not to circulate colder air inside the house prematurely. So when the condenser is heated to the level that is they have decided as optimal for extracting heat from the condenser, the fan comes on. So it will switch from a slow speed to a higher speed if your furnace is equipped to do it. Okay? So when it comes to higher speed, it extracts the heat. The room temperature goes up. Now they will shut it down at 20.1. The older controllers will go 22 to 18. It has a more wider swing. The newer ones come in pretty quick. Okay, it shuts the system off. When it shuts the system off, it switches off the gas supply first. When it switches off the gas supply, obviously flame will die. Okay, but the fan will continue to go at a higher speed, or the high speed at which it was operating, for maybe 1 or 2 minutes to extract every bit from the condenser which is hot and circulate that heat inside, and then it will shut off. And the cycle will keep repeating up and down. The same thing happens in your dryer. Okay? If it is an old clunker, the technology I'm talking about is not there. If it is the new one, well, you throw in a certain load, it's measuring the humidity at the exhaust. Okay? So you don't put 30 minutes, 45 minutes, or 1 hour for a fixed interval. You set it, well, I want it to be heavy duty or low duty or high duty, or there are many options. Then what it does is, there is a pre-programmed time inside but that pre-programmed time is also getting a feedback from the humidity sensor. So if your clothes normally would have taken 1 hour, and for unknown reason, at the end of 48 minutes, your clothes are dry, as indicated by the humidity on the exhaust. We will shut it down, saving you some energy bill. Okay, and the level of sophistication of this systems in terms of control is becoming more advanced. But this is the grudge I have with the modern appliances, modern electronics. Yes, they are packing all kinds of fancy uh, options, but they are cheaping out in making the box and the motors and so on not as rugged as they used to be. So you have premature life failure of the system, the mechanical and other things, and sometimes even the controller fails. Okay, so on one hand, yes, it's going up in terms of sophistication, but they are not building things as solid as they used to be. Okay? So I've given you the example of the home heating system. Now I am going to go with a case study for a furnace control, which has got not all of it, but majority of it. So in this case, we have a furnace which is going to preheat forging blocks. And the whole stuff is powered by natural gas. Uh, the problem statement must be understood very clearly. So furnace heated by natural gas. So natural gas must be controlled. You don't put natural gas inside the furnace all the time. You have a shut-off valve for the entire house that's always on unless there is an emergency. But within the furnace, there is another valve, which is electronic, which is going to be controlled by the controller that we are going to develop. Okay. Conditions are when you want the furnace to start, what do you have to do? You must open the gas valve, allow natural gas to come in. Then you must start an ignition system right away. The ignition system is sparking, so it has its own electronics. But as a safety, something is being looked at the flame. Either the flame doesn't come or flame comes and then dies. What should you do? If the flame dies, retry. Get the ignition back and make it ignite again for a period of time. The ignition should be coming in only for some programmed time, 6 seconds, 5 seconds, or whatever, right? So first time it went for, let's say, it is programmed to go 6 seconds, but at the end of 3 seconds, the flame came on. So it should automatically quit when the flame comes on. Then magically or some disaster, the flame went down after it came up. So controllers say, oh, there is no flame. The flame went down. Come back again and ignite. Okay? Keep the gas valve open. When the gas valve is open, obviously gas supply is coming. So all this is happening very fast. So if it is successful second time and the flame sustains, ignition has no role. It should be the moment flame arrives, ignition should go. If in the second time, well, the flame didn't come, gas valve was open, accumulation of gas inside, a spark is trying, but something is wrong. The flame is not coming. Shut the whole thing down. First thing you want to do is shut the gas valve. That means there is no more gas, unburnt gas inside. Okay. So the whole operation shuts down and you must send an alarm. That I tried 2 times, nothing happened. Okay. So that's the problem statement. There are lots of bells and whistles here that are to be put into picture. But I am going to simplify the problem. There is no flame sensor that is, I'm not going to make it complicated to understand the problem. So I have a P, power, not momentary on, off, or maybe momentary on, off, we'll see it. The status is when the power is on, it is 1, when the power is off, it is 0. Then there is a flame. That means there is a flame sensor looking at whether the flame is coming or is sustained. 1 when it is present, 0 not present. So I'm going to take the minimum P and F as inputs. And then we have the outputs. The gas valve, well, let's assume it's a stepper motor driven valve. I mean, it opens and closes. Okay, like a bell valve. Fully open, fully closed. Only 2 positions. 1 or a 0. That's the output. Ignition, spark, not spark. 1 or a 0. Okay. An alarm, flash or siren or whatever. When it is flashing, something has gone wrong. 1, it is not flashing. Everything is good. 0. So right now, let's take the very minimal input output combination. Okay, so in the previous case, we had a 1 input, 2 outputs. Now we are going 2 inputs, 3 outputs. Okay, so again, we can go through I will show you the truth table solution, and once I finish the logical problems. If you follow this logical way of analysis, that is going to help actually if you want to go to the truth table, because this is the most critical process. So I have put in 5 variables, out of which 2 are inputs and 3 are outputs. These are the most essential, and you can add more and more. Okay, you can look at the quality of the exhaust and some of the modern furnaces. There is a intake. If you looked at the old furnaces, there will be an intake from outside the house through your intake duct in the house. That means if it is minus 30, minus 40 outside, yeah, it's bringing in cold air. That's why you would see some of the intake ducts very close to the outside wall, heavily bundled up with thermal insulation. Okay, but you can see them ice up. Okay, warm air condenses on cold surface. Very simple. Okay, in the modern stuff, there is a damper which can proportionately open close. If it is minus 30, it's not letting all the air. But that problem is completely taken out in the high efficiency furnace, where the flame requires always good amount of oxygen or air to burn. So there is a separate intake which doesn't get mixed with anything else. It doesn't go into your distribution system at all. It comes straight to the flame and then goes out as exhaust gas. And in high efficiency furnaces, I'm saying how you can actually add more inputs and outputs. The flame, when it burns, when there is a flame, the byproduct is water. to some extent there is a condensation coming out. That has to be pumped out. So you also have a pump, and the pump will have a level sensor, which will push it out when the chamber is full. So more stuff can be added to make the problem more bulletproof, if that's what you want. Okay, I got only 2 minutes left. So the next step is to put logical statements as to for each of the output, what are the conditions required. And then this problem also is going to go through the backward route of constructing the hardware and then transferring it to a logic network diagram without going through the truth table. You can also go through the truth table, and I will show you the truth table after I finish this. Any questions? Okay. Usually, I don't expect you to ask me questions right away, but when you read it, there may be some more questions that will come up. So you can always ask me next time. Don't wait until your midterm test comes up to ask questions. Just to review it once to make sure you get it. Okay. So just the announcement, formal announcement again. Not this Friday. By next Friday, I need the part program as well as your complete, not the report at all, the Mastercam files for the lamp base, so that Dave and myself can look at it, prepare everything for you to see when you come back, so that majority bulk of the work in terms of machining is ready. Okay. So those of you who are in the Thursday's lab slot, I will see you this afternoon. Okay. See you.